a high wavelength. So this shows us kind of a good picture of the relationship between wavelength and frequency. When this one has a high wavelength, its frequency is low. So when one variable is high, the other one is low. This one has a high frequency, but its wavelength is small. So when one variable is high, the other one is low as far as wavelength and frequency go. I know it's a little frustrating. You've got to get to know new letters and know what the letters mean. But yeah, do know that that is the wavelength, that's the frequency. H is a constant value times the frequency. All right. Almost done already. This one I just wanted to leave in to show you that what we can actually see with our eyes is just a little tiny part of the spectrum, the big light spectrum. When we were able to see those distinct bands of light, there was only a couple of bands out of many that electrons will give off. There were a bunch of bands in the ultraviolet that our eyes just can't see. And there were several in the infrared that our eyes just can't see. So we would need other instruments to find all the different electron transitions for an atom. Above this, as you see, by the way, this scale tells us the frequency is going up as we go to the left. Now, remember, as frequency goes up, the energy goes up also. Remember, E equals H times nu. Means that frequency and energy are directly related to each other. If you have a high frequency, you got a high energy. So over here, X-rays, gamma rays, those are very high energy waves. Gamma radiation, that thing right there is a Greek letter gamma. Gamma radiation is often observed when a nuclear atom decays, or a nuclear substance decays. There's a lot of concern about gamma radiation where you have like nuclear power plants, nuclear medicine, that kind of thing. They have to be very careful to not expose the workers and the patients to much radiation. So you got gamma radiation all the time. Notice, as the frequency goes up to the left, the wavelength, which is on the bottom, this scale is going up as we go to the right because they're inversely related. Over here is a high frequency, over there is a high wavelength. So over here we'd have very long waves. Radio waves are long, long waves. They're like in the order of whole meters, or sometimes even kilometers or megameters. So one wave would take up like 1,000,000 meters. That's right there. So yeah, it's kind of funny to think that, but they're all the same speed. All light waves are the same speed. And just another picture of the possible jumps for electrons, because like this I think shows 5. 1, 2, 3, 4, 5. Yeah, there's 5 energy levels. And this is not even any going to the first energy level. All these jumps are going to the second energy level. You can go from 3 to 2, from 4 to 2, from 5 to 2, from 5 to 3, from 4 to 3, like that. You can have all these different jumps, so that would correspond with lots of different bands of light on a spectrum. Now I'm going to stop here with this picture, and again, nothing to write down. Erwin Schrodinger was the person who came up with the idea about how electrons are described that we still currently use. Our picture of the atom and the way its electrons behave goes back to 1925. Erwin Schrodinger, it was interesting, he described electrons purely as waves. He didn't consider them particles at all. So he came up with this wave equation, which is weird. We know electrons are particles. They have mass. They're things. But he was treating them as if they're waves. And he came up with these wave functions to describe electrons, very complex. And so tomorrow, what I'm going to do is just kind of narrow that down, and I'll give you what you need. To do a full study of Schrodinger would be like a third-year college course. In chemistry program, it would be called physical chemistry. It's a class that you take. And about for half the class, you go through the Schrodinger model of all the calculus that was involved. Pretty cool. But I learned it then, and I did very well at it, but now I've forgotten all of it because we just don't use it in high school. So I can't remember. It's just like all the French I learned. I took French, AP French, French in college. I don't remember any French. Sorry, shit time there. Don't remember. So anyway, yeah, we'll pick up with the Schrodinger model, which is, you know, the current modern model of the electron.